Jai Hind to all. Myself Uma Sharma, Assistant Professor in EC Department of Ajay Kumar Garg Engineering College. Today in this lecture, I'll discuss one of the complex topic of integrated circuit design for the subject code AKGEC 501. So this is the topic of Unit 1. So the content of this lecture is the basic circuit diagram of 741 IC, which include bias circuit, short circuit protection circuit, input stage, second stage, output stage, and the different device parameter. Mainly in this lecture, I'll focus on this topic, that is DC analysis of 741 IC. The slide shows the content of Unit 1. Basically in Unit 1, the first topic is basic introduction of 741 op-amp circuit, then DC analysis, then AC analysis, which is also known as small signal analysis, then frequency response of 741 IC, and here you will see the frequency response and slew rate of 741 IC. The overall gain calculation will also be taken care in under this topic. So if you have already shown the circuit diagram of 741 IC, it includes a number of transistor. This is the circuit diagram for 741 IC, where you can see there are 24 transistors, 11 resistors, and the 1 capacitor. So what we have to do for the given circuit, which is shown in the slide, we have to calculate DC current and DC voltages, and the calculation of DC voltages and current is known as DC analysis of the circuit. Later in the in this unit, the small signal modeling will be done to calculate the gain, input impedance and output impedance of 741 IC. So just look at the circuit. One by one we will discuss the DC analysis of this complete IC. But it is like very complex to study the whole IC in one go. So I'll divide this circuit into 5 parts. That includes biasing circuit, that includes input stage, intermediate stage, output stage, and short circuit protection circuit. So basically I'll divide the circuit into 5 parts, and one by one we will discuss the DC analysis. So before start the DC analysis, first you should know the basic parameter, device parameter of 741 IC, so that we can do the calculations. So basically 741 is manufactured by the Fairchild Corporation. There are different companies which produce or which manufactures the 741 IC or operational amplifier IC, but specifically 741 is manufactured by Fairchild. It consists of 24 transistors, 11 resistor and 1 capacitor, as you have already seen in the previous slide. Then the IC requires 2 supply. Basically it is dual supply integrated circuit, where positive supply, that is plus VCC, and negative supply minus VEE is used in the complete IC package. So normally the value of VCC is used in the circuit is plus minus 15 volt, and although the IC is capable of operating at much lower value, that is up to plus minus 5 volt, and if we talk about the higher side, then it can work up to plus minus 22 volts. So before moving to the complex circuitry of the 741 IC, first we should know what is the block diagram of operational amplifier. So for operational amplifier, there are 4 important blocks. One is input stage, then intermediate stage, level shifting stage, and output stage. Basically the input stage is a differential amplifier, and here you can see that it is dual input balanced output differential amplifier. As we know that in this symbol there are 2 terminals, one is negative, one is positive. There are 2 supplies, one is plus VCC, second one is the minus VEE, and there is one output terminal. So in this block, this positive terminal is represented as non-inverting input terminal, and this negative node is represented as inverting input terminal. Basically, this block consists of differential amplifier. Next is the intermediate stage, and in intermediate stage there are obviously there are two inputs. So it is dual input unbalanced output differential amplifier, means output is taken at a single node, just like this. Input is applied using two terminals, so that's why it is dual input, but output is taken from this single node, so that's why it is known as unbalanced differential amplifier. So it still is a differential amplifier, but the use of this intermediate stage is to provide the gain. So this stage is also known as gain stage. Next is the label shifting, because we have taken the output from single terminal. So to shift the output label of the signal, we will use label shifter over there. And again, this label shifter is made up of transistors, and basically this is designed using the emitter follower using the constant current source. So this is another block, and these block we will see in the circuit of the 741 IC. The next is the output stage, which is a class AB power amplifier, because at the output node the output is taken, so we have to take care of that. So here the power amplifier is used to design the output stage. So these are the 4 blocks, and in the slide shows the usefulness of these blocks, like input stage used to increase the CMRR, it also used to adjust the high gain, it also provide the input impedance which is very high. So the advantage of using these stages has been shown in the slide. So now just see the circuit, and here I will tell you how to divide this circuit into these 4 blocks. So first of all, let's have the look. This circuit is a Vidlar current source. You can see that this is Vidlar current source. Here you can see that the transistor Q12 and the transistor Q13, these are used to form a current mirror. Again you can see that there is another current mirror consisting of Q8 and Q9 transistor. Again this is a current mirror. So there are 2 current mirrors and 1 Vidlar current source. So these are the current sources which are used to bias the IC or to generate the current, so that the current, the required current can be provided to the input stage, intermediate stage and output stage. From these current mirrors you can see that the Vidlar current source is generating a current which is provided to the another stage. Similarly, the Q12 and Q13 transistor are forming a current mirror and generating a current which is provided into 2 different circuits. One is Q13A. So now in this circuit, the circuit which is shown in the red color box are representing the biasing circuits. In the complete circuit diagram, whatever I have circle in the red are known as biasing circuits. Now come to the first stage, that is differential amplifier. So here you can see that Q1, Q2, Q3 and Q4. These transistors are forming differential amplifier with level shifting stage. Here Q1 and Q2 are the differential amplifier, and Q3 and Q4 transistors are used to shift the output of the differential amplifier. So these transistors are known as level shifter transistors. Whereas Q5, Q6 and Q7 along with the resistor R1, R3 and R2 are used as active load to the differential amplifier. So, in conclusion, I can say that transistor Q1, Q2, Q3, Q4, Q5, Q6 and Q7 are forming input stage with level shifter. So, this is known as input stage. This diagram is known as input stage, here to here. Now, this is the circuit which is having second stage, output stage and short circuit protection circuit. So, till now we have discussed biasing circuit and the input stage. Now, just see the Q16, Q17 transistor. This Q16 transistor is known as emitter follower or the common collector amplifier, because here we are taking output from the emitter node. This is the emitter of Q16. So, basically this is used to provide the perfect impedance matching between two stages, input and the secondary stage. So, the use of this Q16 is to provide the impedance matching. Then Q17 transistor is a common emitter amplifier which is used to increase the gain, because we know that operational amplifier is having very high gain. So, to increase the gain, here Q17 transistor is used as a common emitter amplifier. The circuit is internally compensated. So, this CC capacitor is added in the circuit. You can skip that for the DC analysis. Now, for the biasing of this second stage, which include Q16 and Q17 transistor, we require a current, and this current is provided by Q13B transistor, and Q13 is a bilateral transistor where two collector terminals are used. Then next is the output stage, and I have already told you output is a power amplifier, and this power amplifier is used is designed using the class AB amplifier. So, for class AB amplifier, the transistor Q14 and Q20 are used. So, transistor Q14 and Q20 are the power amplifier transistors, that is the output stage, and the current for the output stage is provided by Q13A, which is forming a current mirror with the Q12. Now, the remaining circuit Q15, Q21, then Q24 and the Q22. These are the transistors along with the R6 and R7 resistor are used to protect our IC from the short circuit. So, if there is any short circuiting in the IC, then these transistors will be on and they can protect our IC from the damage. Otherwise, these are the transistors which are in off state. So, always these transistors Q15, Q21, 24 and 22 are off. Remaining transistors are Q18 and Q19, which are used to enhance the base to base voltage of Q14 and Q20. These are the output transistors, and the area of these output transistors are more. So, to increase the base to base voltage between these two transistors, Q18 and Q20 transistors, Q19 and Q18 transistors are used. So, this is the description of 741 IC. Here I have divided this circuit into the 5 parts, and for short circuit protection circuit, all the transistors are off. That means the current in these transistors is equals to 0. So, Q50, IC15, IC21, IC24 and IC22 is equals to 0. These 4 current component will be equals to 0. So, now we have to calculate the other current components from Q1 to Q24. So, first of all, let us calculate the biasing. So, biasing circuit I have already told you. So, to calculate the biasing current, first of all, we have to solve this first branch where the reference current is generated using the Q12 and Q11 transistor. Here a R5 resistor is used, the value of R5 is 39 kilo ohms, and to calculate this I reference, just apply the KBL. So, now you can see that if I apply KBL, that is equals to VCC minus, because in Q12 these terminals are shorted. So I can say that the base and the collector are connected to each other. So the base, this is the voltage which is known as VEB12 because this is PNP transistor. So VCC minus VBE12 minus, again these are shorted. So the voltage between these two terminal will equals to 0. Here also this voltage is equals to 0. So VCC minus VEB12 minus VBE11 and minus minus plus VEE is equals to I reference into R5. So from here you can calculate the value of I reference. So this is the equation, and this equation I have derived from the KBL, right from this node to this node. So just by putting the value of VCC, VEE which is equals to 15 volt, VEB and VB12 is equals to 0.7 volt. The I reference can be calculated, and this I reference is equals to 0.73 milliamperes for 741 IC. So for the 741 IC, the reference current which is produced by the transistor Q12 and Q11 is equals to 0.73. Now this current is going to the input stage through a Widlar current source, because the current required to bias the input stage is very less. So to convert this 0.73 milliampere current, we need a circuit by which we can reduce that current component. So you know that the Widlar current source is used to reduce the current. So this reference current is 0.73 milliamperes. Now using this Widlar current source, we can reduce it in the microamperes. So just in this slide, the circuit is shown for Widlar current source, and this circuit I have taken from the complete 741 IC diagram. So here also you can calculate IC10 just by apply the formula for Widlar current source, or from this diagram you can see that the VBE minus VBE11 minus VBE10, VBE11 minus VBE10 is equals to IC10 into I4. Just apply KBL in this loop, so you will get this expression, and here this IS11 is equals to IC10. This is given in the device parameter of 741 IC. The value of reverse saturation current IS is also given for NPN and PNP transistor. So now you can calculate the value of IC10 into R4 just by calculating VBE11 and VBE10, and we can calculate VBE11 and VBE10 using very simple equation, like just write IC11 is equals to IS, this is the transistor current equation, IS11 e to the power VBE11 by VT. So from the previous diagram you can say that IC11 is what? IC11 is what? Actually it is equals to I reference. This is nothing but IC11. So I can write IC11 is equals to I reference, and hence that can be given as VBE11 is equals to VT ln I reference upon IC IS11. Similarly, you can calculate VBE10. Similarly, VBE10 can be calculated, and that is equals to VT ln IC10 upon IS10, and you if IC11 is equals to IC10, so you will get this expression, and again this expression is equals to IC10 into R4. So just by putting the value of VB11 minus VB10, you will get this equation, and just by putting the value of VT I reference R4 in the equation, you will get IC10 is equals to 19 microampere. So this is the current which is used to provide the input stage. So from this at this point we have calculated the biasing current of input stage. Now come to the circuit of input stage. So up to this point we have solved the half of the biasing circuit. So now let's see what are the current component for the input stage. So I have already told you this is the circuit diagram for input stage, which include differential amplifier, level shifter and the active load. So now you can see that at this point X, the current is IC10, and here the current mirror is used to mirror that current to provide current to the differential amplifier. Q1 and Q2 are identical. If Q1 and Q2 are identical, that means the current in Q1 and Q2 is equal, and if I assume that the current in Q1 is capital I, then this current in Q2 will also equal to capital I. So this is how I can write this is 2 times of I. So the output current of this current mirror is 2I, and now let's see, this current is flowing in Q1 transistor and moving towards the Q3, and the base current of Q3 let's equals to I upon Vp. Vp is the current gain of the P type transistor, because Q3 is PNP transistor, and definitely this beta P is very greater than to 1. So we can neglect this base current. If I neglect this base current, so I can write the current which is coming from the Q1 is equals to the current output of the Q3 transistor, and similarly I can write the current in Q2 is equals to the output current of Q4. So this is how I can write the IC1 is equals to IC2, and that is equals to IC3, and that is equals to IC4, and is equals to capital I. Now let's say, suppose this current is nearly equals to 0. It means this current IC10 is equals to 2 times of I. If this base current is 0, it means this is the same current, 2I. So I can equate 2I with IC10, and this is how I can calculate the value of capital I, which is equals to IC10 divided by 2. And in the previous slide, we have calculated the value of IC10, which is equals to 19 microampere. So this is how we can calculate the value of IC1, IC2, IC3 and IC4. So this you can see from this slide here, this value we have calculated, and that is equals to 19 by 2, 9.5 microamperes. Now to calculate the value of IC 5, 6 and 7, let's have a look to the circuit, this load circuit, and here this IC3, this dotted line is connected with this dotted line, and this dotted line is connected with this Q6 transistor, the collector of Q6. So that means the collector of Q3 is connected with the collector of Q5, and the collector of Q4 is connected with the collector of Q6. And if again considering that the base current of Q7 is 0, this IC3, which is equals to capital I, definitely will equals to the collector current of Q5, that is IC5. So from the diagram, it is obvious that IC3 is equals to IC5. Similarly, the IC4 is equals to, if this base current is 0, then I can equate it with IC6. So again, I have calculated 2 more parameter, that IC5 is equals to I, and that is equals to IC6. Now, the only current component which we have to calculate is this current, IE7 or IC7. Because the base current of this Q7 transistor is 0, it is 0. So that means I can write the IE7 is equals to IC7. Here I can write IC7 IC7 is equals to IE7. So now to calculate this value IE7, just see that this current, just apply KCL at this node. So you can write that IE7 is equals to this I upon beta n plus I upon beta n, that means 2I upon beta n, plus the current flowing in this resistor R3, which I can write I R3. So you can apply KCL at this node like this. Now you have to calculate this IR3. So to calculate IR3, just apply KBL in this loop. And if I write the equation for this KVL, for this loop, you can write like this: minus VEE plus IR3 into R3, and this is the voltage VBE6. So that is minus VBE6 minus this current I, capital I into R2, and this minus VEE will become plus VEE, and that is equals to 0. So these two terms will cancel out. So from here you can calculate the value of IR3, this value, and you can have this equation like this. So IC7 is equals to IE7, and that is nearly equals to 2I by beta n VBE6 plus IR2 divided by R3. In this equation, we know the value of beta n, we know the value of I, R3, R2. The only term which is unknown, that is VBE6. So VBE6 we can calculate using this equation, and this is equals to VT ln I upon IS. So just by putting the value of VBE6, just putting the value of I and IS in this expression, we can calculate the value of VBE6, and which is equals to 517 millivolts. So now the calculation of IC7 is very simple. That is equals to 2I by beta n plus 517 millivolts plus I into R2 divided by R3, and this equation will produce 10.5, sorry, that equation will produce 10.5 microampere current. So for the input stage, we have calculated all the current component IC1, IC2, IC3, IC4 and IC5 and 6 are equal, and that is the value is 9.5 microampere. For IC7, the value is 10.5 microampere. So this is how we can do the DC analysis of 741 IC input stage. Similarly, we can apply this concept on second stage, output stage, and in the upcoming lectures we will see how to calculate the value of different current components of second stage and the output stage. So for this lecture, this is all from my side. Thank you so much.